Hello students, in this video we are going to discuss the guided study for learning target AD2, the first derivative test. In this learning target we're going to use the first derivative test, which we will abbreviate as FDT, to locate critical points, classify maxima and minima, and determine intervals over which a function increases, decreases, or remains constant. For this guided study, I want to review the textbook example 4.13. You can pull this example up in the online version of OpenStax Calculus by loading up the book, going to section 4.3, and scrolling through just a little bit. It is in the Locating Absolute Extrema section. I really want to emphasize the importance of that problem-solving strategy that is in that same section, Locating Absolute Extrema. The problem-solving strategy is called locating absolute extrema over closed intervals. And in this case, we have two examples with closed intervals. However, we're going to emphasize that in class, in lecture. For now, I want to just discuss functions like negative x squared plus 3x minus 2 and x squared minus 3x to the 2/3 by not only using the first derivative, but also by looking at the graphs. So in this case, I have graphed in Desmos the example A, negative x squared plus 3x minus 2, and I've graphed it in red over its entire domain, and I've added this little black portion here just to show you what the 1 to 3 looks like. And we're going to pick up talking about this example in lecture. For now though, this guided study really goes really well with the lecture I'm going to give for this section, so please pay careful attention. I've posted the blank notes for this, but really it's just the example from the textbook, so you can kind of skip them if you want and just write down this example, write down what I'm talking about. Towards the end as well, I'm going to show you another kind of a really important point about the first derivative test using quadratics, using polynomials of degree 2. But first, let's talk about this example, and again, looking at this example. Please pause this video and take out your calculator and graph this function. Make sure you can see the same thing I can see. In the TI-84, you will see the function over its entire domain. I don't believe there's a way to go in and restrict it to be a closed interval. I could be wrong about that, but for now, we're just going to focus on this plain old polynomial on its entire domain. And I want to remind you of things that we've said in the past, words that we've used, phrases that we've used. Remember, math builds on itself. So in the past, I've displayed or told you things like when f prime of x equals 0, there is a horizontal tangency. Now we're going to see why that's important. Specifically in this case, where there's a horizontal tangency, and we don't need to know right now exactly what that value is, I just want to emphasize that where that maximum point is, there's a horizontal tangency. This function, if we extend it forever in both directions, is a function y equals a constant value. And we'll find that constant value in a minute. For now, I just want you to focus on the fact that this is a function with constant derivative. The derivative of y equals a for any constant number a equals 0. At that point, on the curvy function, we see there's a horizontal tangency, but what we also see is that point is the biggest point possible on this entire function. We call this a maximum. Now, we will get into in lecture exactly how to know it's a maximum without seeing the graph. We're going to use the fact that we talked about when the first derivative is positive, the function's increasing, and when the first derivative is negative, the function is decreasing. Notice how this function changes behavior around that maximum. On the left of that maximum, this function is increasing. And on the right of this maximum, the function is decreasing. We're going to use that observation and that fact in class to determine minimums and maximums without the graph. But for now, we're looking at the graph. And again, where f prime equals 0, there is a horizontal tangency. We see where that point is. We can't quite tell exactly where it is in terms of the coordinate yet, but we will be able to when we take f of x equals negative x squared plus 3x minus 2 and differentiate it. F prime of x in this case is negative 2x plus 3. If you don't know how to find that, please go review Learning Target D4. And when we set that function f prime of x equal to 0 and solve, we get negative 2x equals negative 3, or x equals negative 3 divided by negative 2, which is positive 3 halves. What we're finding is the x value of where that maximum point exists. So if I want to find the full-on coordinate of that maximum, I need to evaluate f at 3 halves, not f prime, but f. F prime at 3 halves equals 0. F at 3 halves is negative 3 halves squared plus 3 times 3 halves minus 2. And this comes out to be 1/4. Now, I let you use calculators in my class, so I highly recommend that real quick, pause this video, take out your calculator, just type this in and make sure that you can get this value. The key here is this negative applies after you square the 3 halves. If you put the negative inside the operation square, you won't get the right answer. So make sure you're able to use your calculator to do this. And again, I want to emphasize that to find that coordinate, I had to plug the critical point. That's what this is called. So spoiler alert, this point right here is called a critical point. This is in the definitions as well that you should be focusing on when you're doing your reading this time. A critical point, and we'll define this precisely in class, is any point where f prime of x equals 0 or is undefined. And actually, I'm gonna go ahead and write that. I want this in your notes. A critical point of f of x is any x value in which f prime of x equals 0, or, and this is very important, f prime of x is undefined. So to find critical points, take the derivative of the function, evaluate the function for y equals 0 or f prime equals 0, so find those x values, and also pay attention to points where f prime is undefined. We're going to see that in example B. So in our case, and we see this visually, this is a maximum and this is a point where f prime equals 0. At this stage, open up your Desmos guided study. I've got another example similar to this there. I want you to practice finding the critical point, the y value of the critical point, and visually recognizing whether it's a maximum or a minimum. We're going to learn again in class that when the behavior of f is increasing, decreasing around the critical point, it's going to classify it as a maximum. But for now, I want you to be able to just recognize this. As well as going into example B, where we see the square root function appearing in f. What's going to happen when we take this derivative, and actually let's just go ahead and scroll into that example. I have a picture of the graph here again, and I have in black this graph over 0 to 2, but I really want to focus on the whole thing because another useful point of this one is there's another critical point over here. And there's actually a critical point here, which we're going to talk about in a second. First, let's differentiate it. This is f of x equals, what's our function? X squared minus 3x to the 2/3. And I like this example as well because it really requires you to review AD4 if you haven't, not AD4, but D4. To find this function's derivative, review the power rule. Remember, the power rule is dx of x to the n equals nx to the n minus 1. We've got two power functions here, the square power function and the 2/3 power function. So this is f prime of x is 2, because I'm bringing it down out in front, x to the 2 minus 1, 1. And the next one is 3, because 3 is already there, times, bring the power down out in front, that's 2/3, x to the 2/3 minus 1. And watch out for this. 2/3 minus 1 is 2/3 minus 3/3, which is negative 1/3. So f prime here is 2x minus 2, because I have 3 times 2/3, 3's cancel, times x to the negative 1/3. That is f prime of x is 2 times x minus 2 over x to the positive 1/3. And this is really important. This is really important. If you have not gotten your D4 point on a checkpoint yet, chances are you're missing fractions, fractional powers, or negative powers. Remember, if something's in the denominator like this, it's a negative power. Also, don't forget the exponent rule for fractional exponents. The nth root of x to the m is x to the m divided by n. So we could have written this as the cube root of x squared. If I gave you that on a checkpoint and asked you to differentiate it, you would need to translate it into the fractional exponent and then differentiate it according to the power rule. But what I really want to point out here is at x equals 0, f prime of x does not exist. So this point here is a critical point. We have one at x equals 0 because f prime d and e is undefined. And then we've got 2 more here at these pink points. We can visually see that they are negative 1 and 1. And again, that's another reason why I want to start with the graph in this section, because you can see it. You can actually visualize these points. Negative 1 and 1 are where you're expecting f prime to equal 0 because there are horizontal tangencies there. And you can also see that y equals negative 2. So when you're first doing these, specifically with this guided study, I want you looking at the graph, and I don't want you answering the question until you can make the math match what you see on the graph. Obviously, you could just use the fact that you can see it on the graph and answer the question, but you can't do that on a checkpoint. I'm going to expect you to show me this work. Again, starting with the maybe more obvious critical point where f prime is undefined, remember, because you can't divide by 0, and then finding the one where f prime equals 0. And this requires a little bit of algebra. So f prime equals 0 when 2x minus 2 over x to the 1/3 equals 0. And you can do this a couple of ways. I recommend isolating this term over here. So subtract over the 2x. And then I would personally try to annihilate that denominator and multiply by x to the 1/3. If I multiply by x to the 1/3, then what I have is negative 2x times x to the 1/3 equals 2 over x to the 1/3 times x to the 1/3. The idea here is if I annihilate this denominator that's kind of in my way, it's kind of preventing me from finding my 0, I will then have a more simple equation that I can then solve for x. But you have to be careful here because this is an exponent rule. Remember, if no exponent is written, it's implied to be a 1. The exponent rule here is if I have 2 bases that are equal and I have them raised to powers that are possibly not equal, then I can add the powers. So we have x to the 1 times x to the 1/3. According to this rule, that's going to be x to the 1 plus 1/3. So x to the 1 plus 1/3 is x to the 3/3 plus 1/3, or x to the 4/3. So I have a negative 2, x to the 4/3 equals 2, or x to the 4/3 equals, I'm going to divide here by negative 2. That's negative 1. And the reason I love this example is because there's a lot of little algebra tricks here that you need to know, right, that you might need a refresher on. And the key point here is practice more problems than you ever will need to do so that no checkpoint question is a surprise. And if you look at the guided study, I have a lot of problems from this section listed. I highly recommend you do every single one of them. I promise you, if you do every single one of them and you can fully understand every single one of them, you will do the checkpoint problems in less than 5 minutes. Maybe not less than 5 minutes, but you'll do the checkpoint problems very quickly if you practice every single example I have listed there. Now, how do I solve x to the 4/3? The key here is I want to annihilate this radical. I want to make the radical go away. It's a fractional exponent, but I can write it as a radical, right? This is the cube root of x to the 4th. Now, if I cube the cube root, I reverse that operation, right? Cube root cubed. If I have n in a root and I raise it to the nth power, what I actually have is x to the 1 over n times n. That's x to the 1. So if I annihilate this cube root, what I have is x to the 4th equals, by annihilating the cube root, I have to cube the other side as well, because it's the same as from algebra. What you do to one side of the equation, you have to do to the other. I get x to the 4th equals -1. So now I'm taking the 4th root, just like if x squared equals -1, you'd take the square root, which is a problem, because why? You can't have a even power equal a negative. So that means we made a mistake, and that's fine. This happens. Let's find it. Let's find our mistake. Ah, I see it. Actually, I want everybody to pause this video for a minute, because if I can make this mistake, you can make this mistake, and I'm not going to edit this out. If I can make this mistake, you can make this mistake. The mistake is on my screen. The mistake is in my algebra. I'll even zoom in a little bit to help you find it. Pause this video right now and find my mistake. Now I'm going to tell you where I made my mistake. Again, please pause it and find it. Take the time to do this, because you're going to have to do this for you. You're going to make mistakes like this. This is how math works. You're going to make mistakes like this too. I did not change the negative. And I also want to emphasize the fact that I got down to this point and I was like, whoa, 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 wait a minute. I cannot have an even power equals a negative number. I can't do it. You can't multiply something by itself 4 times and get an odd number. Not an odd number, a negative number. That made me stop and say, okay, let me pause for a minute and figure out where I went wrong, because I did something wrong. And this might cause you some frustration at first, but you'll get used to this stuff. There should have been a negative right here, meaning there should have been a negative right here, meaning there should have been a negative right here, meaning there should have been a negative right there. And I don't have to erase anything. Once I find my mistake, I'm following through and realizing, oh, okay, this equals 1, not -1. -2 divided by -2 equals +1. So unintentionally, this guided study became an exercise on checking your work and figuring out how to fix it, because nothing I said other than that was wrong. This negative just did not get transcribed correctly. And again, you're going to make these mistakes. It happens. It happens to the best of us. So now I'm actually looking for a point where x to the 4th equals +1, which makes more sense. Okay, again, please don't just get on autopilot and not recognize this. X to the n cannot equal a negative number if n is even. If it's odd, it's fine, but if it's even, it's not. And then to solve this, you want to know, and this is like the square root problem, right? If x squared equaled +1, I would take the square root and I would get plus or minus the square root of 1. This happens for 4th powers as well. X equals plus or minus 1. Emphasizing again, make your work match this. I knew what I was looking for, and I knew when I got to a point where I had an even power equals a negative, something was wrong. It's not the problem. It's not the textbook. It's me, right? I just made an algebra mistake. We all do it. So now I found x equals plus or minus 1 because of f prime of x equaling 0 there. Now, this and this appear on the graph to be the smallest points of f, and they are. If you plug f equals, so if you plug negative and +1 into f, you should get -2. I encourage you to do that. But also, If you plug 0 into f, which you absolutely 100% can do, right? F is that. That's not undefined at 0. F prime was undefined at 0. If you plug that into f, you plug 0 into f, you get 0. And we're going to emphasize this more in class, but notice that this point appears to be the maximum within -1 to 1. So within -1 to 1, this is the biggest point on that graph. This is going to be called, and you don't need to worry too much about knowing this just yet, a local maximum. These will, for our function, be called an absolute maximum. Local, we'll talk about in class, but I'll just say it, means within a certain range of x, this is the biggest. Within a certain range of x, that point is the biggest. It's not the biggest, because there's points out here. On the restricted domain, however, it is the biggest, and I want you to review the textbook example of that as well, because the textbook example emphasizes that this is an absolute max on 0 to 2. We're going to talk a lot more about that in class, but for now, I want you to recognize, looking at this graph, I'm expecting x equals -1 and x equals +1, where y equals -2 to be minimums, or at very least critical points, and x equals 0 to also be a critical point and some type of maximum in our case. Go to your guided study now. I have another example that's similar to this one, where all I'm going to ask you to do is find the critical points. And I also want to emphasize one more thing about cubic functions, third-degree polynomials. So just a quick note, for a quadratic function, like example A, we went from f of x equals x squared plus something, so we went from a power of 2 to a first derivative 2x plus something, a power of 1. When we had the power of 1, there should only be one critical point. Okay, so we've got functions that are doing something like this, or even this. Doesn't matter at this moment exactly what's going on. There's only one point where you have a horizontal tangency. Recognize that the reason you go from power of 2 to power of 1 is because you're taking a derivative, and the derivative goes down in power. For cubics, which we'll see some examples. Actually, I'll put an example in the guided study for this, and I want to see how you do on it. You're going to have f of x equals x cubed plus something, and when you take the derivative, it's going to reduce in power to 2. Now, quadratic functions, when you set f prime equal to 0, have two solutions. Cubic functions, the functions, look something like this. For these cubic functions, you have two little bumps. You're going to have two critical points there. So in the guided study now, look at the third question, which is going to be a cubic polynomial. I'll put the graph. I want you to practice taking the first derivative of cubics, factoring and solving them set equal to 0. So the guided study, you're going to focus on only identifying critical points. I mean the Desmos activity, of course, because this technically is the guided study. So in the Desmos activities, you're going to focus on identifying critical points. I want you seeing the graph, and I want you kind of sizing up, like, what do I think? Is that a maximum or a minimum? Have that like in the back of your mind, because that's going to matter in class and lecture. But for now, just identify those critical points. And for the code word I'll ask for in the last question, go ahead and put tree frog. Tree frog is the code word for the fourth question in the guided study. And I will see you all in lecture. Thank you very much.